Welcome to this video in which we will discuss some common FTD examples. The FTD equation transforms the discrete time samples xn into its frequency representation denoted by x e to the power j theta. The discrete time samples xn are obtained by sampling a continuous time signal xt with the sampling frequency fs is 1 over ts samples a second. The relative frequency theta is dimensionless and related to the absolute frequency omega by theta is omega ts. The frequency representation x e to the power j theta is periodic, which is denoted by representing the function variable theta as an exponent. Only one period of the frequency representation is relevant. Usually, one uses this so-called fundamental interval as theta in between minus and plus pi. The inverse FTD transforms the frequency representation x e to the power j theta into discrete time samples xn. Because of the fact that the frequency representation is periodic and depending on the continuous frequency variable theta, the integral is taken over one period. The most common examples that we will discuss in this video are the FTD and IFTD of a delta function, the FTD of a sinusoidal and an exponential decaying function. We will show that the inverse FTD of a block function is a sink. The selection of a subset of n samples from data can be represented by multiplying the samples with a block function. Mathematically, we can describe such a block function by two step functions, un minus capital letter N. We will show that the FTD of such a block function is a so-called Dirichlet function. This is a sink-like function which is periodic. One of the signals that is used most often is the delta function. Because of the fact that this function is only 1 for index n is 0 and 0 for all other indices, the FTD results into 1. This implies that the delta function in time domain contains all frequencies theta in frequency domain. This effect is represented in the figure. On the other hand, the inverse FTD of a frequency domain delta function results also in a constant 1 for all integer values of index n. In other words, the result represents an infinite train of discrete time delta functions. Furthermore, because of the periodicity of the frequency representation, we should realize that a delta function in frequency domain consists of an infinite train of delta functions. Finally, note the difference between a discrete and a continuous delta function. The first one has a finite value for one index, while the second one is infinite at one time instant. From the previous result, it follows that the inverse FTD of 2 pi delta theta results in an infinite train of discrete time delta functions. The other way around, the function 2 pi delta theta can be obtained by the FTD of an infinite train of discrete time delta functions, which writes as the given equation from which the summations can be interchanged. The inner summation is always 0 except for the index n is p, which results in the given summation of discrete phasors. As mentioned on the previous slide, because of the periodic behavior of the frequency representation, the delta function 2 pi delta theta represents an infinite train of delta functions. From this, we obtain the given discrete phasor property, abbreviated by dpp. We can use the dpp property to evaluate the FTD of the discrete time sinusoidal function with frequency theta is theta 0. The first step is to use Euler and write the function as a sum of two discrete time phasors. From the dpp property, it follows that the FTD of the first phasor results in 2 pi times a delta function at theta is theta 0. And the second one is 2 pi times a delta function at theta is minus theta 0. Thus the result of the FTD of a sinusoidal function with frequency theta is theta 0 results in 2 delta functions at frequencies theta is plus or minus theta 0, which is represented in the figure. A plot of a discrete-time exponential decaying function which starts at index n is 0 is depicted in the figure. In this figure, the parameter a is a real positive number in the range between 0 and 1, and un is a unit step function. Using the mathematical description of this function in the FTD definition results in the given summation, which starts, because of the unit step function, with index n is 0. Combining the parameter a and the exponent results in the argument of a summation from which the running index n ranges from 0 to infinity, and the argument is taken to the power of n. This is a well-known geometric series which writes as 1 divided by 1 minus the argument of the summation. The geometric series do only converge when the absolute value of the argument is smaller than 1. Otherwise, the geometric series will diverge. Because of the fact that the amplitude of the complex exponent equals 1, this implies that the absolute value of the parameter a has to be smaller than 1. For positive values of a smaller than 1, a plot of the absolute value of the FTD is given in the figure. For negative values of a larger than minus 1, a plot of the absolute value of the FTD is given in the second figure. The speed of fluctuations in the second sequence of samples with negative parameter a is higher in comparison to the first sequence of samples with positive parameter a. This effect is reflected in the FTD plots. The second FTD plot shows clearly high frequency behavior, while the first FTD plot has a more low frequency behavior. An ideal block function with a cutoff frequency theta c is depicted in the figure. In the path area, the value of the frequency function is equal to 1, and in the attenuation area, the value is 0. With these values, the integral of the inverse FTD equation reduced to an integral of complex exponents with boundaries plus and minus theta 0. Changing the function variable theta of the integral into jn theta leads to the given equation. Using the boundaries and Euler results in an expression which behaves as a sinc function. For theta c is pi over 2, the inverse FTD result is given in the plot. The result is a sinc function which is infinitely long, and the samples are 0 for all even values of the time index except for n is 0. The reason that this function is infinitely long is caused by the fact that the frequency function x e to the power j theta has an infinite steep drop for theta is plus and minus theta c. The plot gives an example of a discrete-time block function of length, capital letter n is 21, which is equal to 1 for time indices n is 0 up to n is 20. In general, a block function can be described as the difference of the two given step functions, and the result is a summation from which the index runs from 0 to capital letter n minus 1, which reduces to the given equation. Taking out half of the complex exponent in both numerator and denominator simplifies the result to a complex exponent multiplied by a function which is a so-called Dirichlet function. The magnitude, the absolute value of the Dirichlet function, is given in the second plot. The phase of the complex function is completely given by the parameter of the complex exponent, which equals minus n minus 1 divided by 2 theta. Thus, the phase plot of this function is a straight line as depicted in the third plot. This ends this video in which we discussed some common FTD examples. Thank you for your attention.